Okay, I think we are live. Welcome everyone to Synergetics stream number 14. It is December 12th, 2021. Today in Synergetics stream number 14, the spirit is summarized as usual by 3 words, and those 3 words are striving, effectic, and tautopony. Effectic, the definition is from Wikipedia, ancient Greek, potentially describes 3 interrelated concepts. 1, a type of skeptic. 2, the practice of a type of skepticism. Or 3, the general state of being given to suspense of judgment. And tautopony means repetition of the same sound. And in Synergetics, we definitely do a lot of tautopony. We're always talking about tets, and there's a bunch of other words and sounds that we repeat a bunch of times. So that's the spirit for today. Let me just fix the captioning, make sure that everything looks good on the stream. So while we're getting started though, thanks for joining. And if you're watching live, please feel free to add any questions or comments in the live chat. Synergetics is participatory, so please do reach out and leave comments. Please feel free to have fun when you are watching Synergetics and learning about this fun area. Today in Synergetics 14, we're going to go over the key memes and themes as we usually do, and then we will be talking about memes and mnemonics, memory devices for Xyz and IVM, Isotropic Vector Matrix. We'll then go to Synergetics, section 402, Tetrahedron as system. Then section 1230, Scheherazade numbers. So first, the key memes and themes. I'm still not seeing the captions update, so I'm just going to do one more change here. Cloud captioning. It's cool when it works, and it doesn't work when it doesn't work. All right, I think that's better. There we go. Make the QR code big. All right. Synergetics is relational, multi-scale, and systems thinking. It's connected to our accessible experience, and it doesn't have infinitesimals or points, lines, and planes, at least in the way that you'll learn about them outside of Synergetics. In Synergetics, we're framing design as an anticipatory cybernetic science and a sort of ongoing interrogative process. Tensegrity is to Synergetics as engineering is to physics. And tensegrity is tension and compression, structural integrity through tension and compression in balance. Synergetics is the geometry of thinking. And that's a lot like the relationship between engineering and physics, where engineering is like the applied and project-based version of physics, and physics often does go off into math or metaphysics or geometry. One of the big ideas in Synergetics is that space has a shape. When you pack balls together, they don't just go any which way. They minimize their free energy and they fall into a certain arrangement. What shape is that? And wouldn't we want to use that as our coordinate system? Another big idea is that structure is a pattern and that pattern integrity can be static or dynamic. We talk about universe as the total scenario. We don't need to say the universe, it's the universe. That's why it's uni. And system is any subsystem. Systems always have shape. That's what we're going to be talking about in Tetrahedron as system. And we think 4D. 4D is kind of like 4-dimensional. It can refer to the 4 dimensions of an extended Euclideanism, as shown here, kind of a geometric interpretation. 4D can refer to space and time. It can also refer to this uniquely Synergetics way of seeing 4D and just thinking about that as our mnemonic, our memory key to all these other ways of 4D that are always happening at the same time. Let's talk about the things that will integrate. So not much has changed here. What are our preferences and expectations for learning and applying Synergetics? How is Synergetics connected to these other areas like free energy principle and active inference and Haeckel's Synergetics and the constructal law? How can we participate in modern synergetics, and what does the future of computational synergetics look like? So there's all kinds of cool links and things that we'll explore. But let's jump right in to the memes and mnemonics for XYZ and IVM. So this is going to be framed in a way like a Hegelian dialectic, problem, reaction, solution, thesis, antithesis, synthesis. So XYZ, this is the coordinate system that many people are familiar with. You have three orthogonal axes, the X, the Y, and the Z axis, and they're all at 90-degree perpendicular relationships to each other. And the shape that is very natural to the XYZ system of coordination is the cube. And the cube, as we all have learned, has an edge length of 1 and a volume of 1. So the surface area of that square on the side is 1, like 1 times 1 is 1, and then 1 cubed is 1. So the cube has an edge length of 1 and a volume of 1. There's also some equations for volume within the XYZ system. So what's cool about the XYZ system? Let's give the devil its due. It's all space filling by itself. The cube is. What's not cool about XYZ? Well, there's a ton that's not cool, actually, but just to list two. The first is that there's no structural stability. There needs to be this implicit or explicit triangulation. Like if you look into your rectangular building, you'll find these cross bracings that are making triangles. So we need to almost subdivide the sides into triangles to provide structural stability because the triangle is the minimum shape. Another thing that's not cool is the edge of the cube is 1, and that makes you think that everything's going to be nice and clean. But then it turns out that actually the diagonal is square root of 2, and that pretty much every shape is either going to have an irrational volume or be basically pixelated. So we get a lot of clean numbers and integers if we wanted to build something that's a perfect rectangle. But then once we step outside the rectangle, we find that there's a lot of irrational numbers and things that we just can't compute that well. What's the reaction? Synergetics. In synergetics, we're going to prioritize and centralize a tetrahedron, this four-sided shape. Here's my desk tet made by Trevor, a brass tetrahedra. And we're not just going to highlight the centrality of the tetrahedra, we're going to actually say that it has an edge length of 1 and a volume of 1, which requires some math and some correction terms relative to XYZ, but we're going to talk about that soon. So what's cool about that? Well, the tetrahedra is the minimum space including polyhedra. So as far as starting places go, it makes sense to do a tet instead of a cube. And also it's omnitriangulated. It's the minimum structural stable unit. So synergetics is pretty cool. And then the synthesis, the solution, is the isotropic vector matrix. What's cool about the IVM? Well, it's all space filling. The tetrahedra themselves are not space filling. They don't take up all space. If you just concatenate a bunch of tetrahedra next to each other, regular tetrahedra. And one of the core memes is that from the isotropic vector matrix, you can get cubes, but you'll never get the IVM or tetrahedra from cubes. So what is the IVM? The IVM is the isotropic vector matrix, and there's a ton of places you can go to learn about this. And this is the core image. Here we have a cube, and inscribed inside of the cube is a regular tetrahedra. The diagonal of the cube, the edge of the tet, is given a length of 1. So that might be called square root of 2 in the XYZ system, but we're going to go ahead and call that edge 1. So it's kind of like a linear scaling factor. It turns out that when we call that edge 1, which is a nice rational number, we get root 2 over 2 as the length of the side of the cube, which is fine. It's just another shape. It's pretty simple, and it's a cool way to measure the sides of a cube. How do we get to from the vector equilibrium to an all space filler? So the vector equilibrium, and I'm quoting here from the synergetic lattice field theory.org. Synergetics vector equilibrium illustrates its construction from 8 tetrahedra situated around a common central point. Each tetrahedron contributes 3 internal edges or vectors and an additional 3 external edges, because tetrahedra have 6 edges, creating a total of 24 internal or radial unit edge vectors and 24 external circumferential unit edge vectors. And that's sometimes shown with more of a square focus, and sometimes it's shown indented. The isotropic vector matrix, so like Maya or the matrix, the isotropic vector matrix, IVM, is defined by the 3-dimensional honeycomb lattice created by a set of tetrahedron and octahedron stacked together to fill space. So tets alone are not all space fillers, but tets and octs are co-space fillers. The left figure shows a small set of 2 layers of tetrahedrons stacked together. This stacking of tetrahedrons includes empty pyramid-shaped regions between the tetrahedron. The right figure shows a set of octahedrons nested into some of these empty pyramid-shaped regions in the left figure. This combined stacking of tetrahedrons and octahedrons can be extended indefinitely to span arbitrary large spatial extents. So just like X, Y, and Z go off in all directions, the IVM is going to go off in all directions. It's kind of like our field that we're doing synergetics in. So sometimes we want to find equivalences back to Minecraft, back to XYZ, but this is like our field. And it also turns out that this has really nice parallels, which we'll explore later, with the close packing of spheres. Here is from Kirby Earner's 4dsolutions.net, talking about isotropic vector matrices. So, crystallography, as traditionally communicated, is inevitably imbued with a strong European bias in favor of making everything cubical or cube-referenced. Ergo, the synergetics approach to closest packing of unit radius spheres as concentric layerings of 10f squared plus 2 spheres around a nuclear sphere, we're going to come back to that, in a cuboctahedral conformation is rarely found in 1900s crystallography books. Rather, we read about the face-centered cubic lattice, which amounts to the same thing. So here I did a little .gif anatomy, .gif dissection, and we can see how this vector equilibrium is going to be superimposed with another vector equilibrium, and that's going to result in a lattice that's cubic. So let's remember, close packing of spheres, 12 of them, around a center sphere. We get like some triangles, and then we also get some squares. So here's the square side, and here's the triangle side. Triangle side, square side. So D shows this center atom, let's call it, and then the 12 close packed spheres. And what's great about this is that every edge length is the same. So it's kind of like the perfect, like, ohm sound of geometry, the vector equilibrium. That's why it's the VE. So we take D, the VE, and then we superimpose an inverted VE. We get this C plus D. This is a GIF. By the way, on Kirby's site, it's a GIF. And from C plus D, in a way that's really similar to how the tetrahedra, one of them inscribed half of the points of a cube, but then a second tetrahedra inscribes the other 4 points of the cube. The 2 vector equilibria inscribe all of the points that you need for a cubic lattice. So in the graphic below, which is decomposed here, we see that the isotropic vector matrices C plus D combine to form a simple cubic lattice. So if no other memes are distilled from this, just know that from the vector equilibrium and the IVM, you get the cubic lattice. But from the cubic lattice, you're always going to be in pixelated Minecraft world, where shapes have irrational volumes. So anytime someone's like, but what about this cool feature of the cubic lattice? Just go, great, we have that. We just do more and we do different. Here's another awesome recent development from Kirby at 4D Solutions, and it relates to finding the volume of a tetrahedron. So check out 4D Solutions School of Tomorrow volume talk, the Python notebook, if you want to learn more and interact with this, but it's pretty cool stuff. Two approaches are provided, the PDF and the GDG, those are two people's names, provided for calculating the volume of a tetrahedron. And so basically you specify the 6 edge lengths, which uniquely specify, except for chirality, which tetrahedron you're talking about. And then this is a function, the PDF and the GDJ, that define the volume of that. So just like we have like height times width times length for a cube, we have a different one that takes 6 arguments for finding the volume of a tetrahedron. And if we put in all ones here in the PDF, we get a volume of 0.11. If we put in all ones into the GDJ, we get 1.0. So that's the one that we want to go with, right? Because we know that we have an edge length of 1 and a volume of 1 in Synergetics. How could these be so different? The GDJ returns a volume in tetravolumes instead of in terms of unit cubes, which have a unit volume of 3. In addition, its unit edges are twice as long, being in sphere diameter versus radii. So qualitatively, this is related to what Bucky said, unity is plural and at minimum 2. But quantitatively, it's related to the idea that if we have the edge length of 1, and then we think about that 1 as the radius of a sphere, then the cube has like an edge length of 2. So if you imagine a sphere at each vertex of the cube, or a sphere at each vertex of the tetrahedra, like 4 closely packed oranges, then we want to give this a value of 1. That's like the smallest possible integer. And so also it's cool because it's like R and then the Ya from Russian. And that is the diameter of 2. So the distance between the two vertices is actually 2 for kissing spheres. And it turns out that if you take the PDF of 2, so that's moving it from an edge length of 1 to 2, and then multiply it by the Sin3 constant, you get a tetravolume of 1. So the PDF is in the XYZ coordination system, but by just making the edge length 2, and then multiplying it by the Sin3, which is a constant variable, then you get that 1 back. Oop. So what is Sin3? Sin3 is defined here very interestingly as the ratio of the GDJ of an all 1 tet divided by the PDF XYZ coordination system of all 2-sided tet. So the Sin3 is the Synergetics constant. It's 1.06. And that's kind of like a scaling factor by which we get between cube volumes and tet volumes. But we also need to mind the difference between edge length of 1 and a diameter of 2. Let's keep learning about the IVM. So this is on the Trim tab mailing list. Dick Fishbeck wrote, "If I didn't post it before, here it is again for posterity. AKA Kirby's, I'm already looking at the Trim tab archives itself as Lionel's notebook, kind of like an archival resource. And these are some of the greatest hits of humanity. Some of these equations. We have Euler in 1700s, finding out about the triangular numbers. We have Fuller in the mid-1900s, finding out about the relationships of the vertices and the tet volumes of shapes of different frequency. We're going to come back to that. And then in 2021, I guess you could say kind of a breakthrough year for Fishbeck et al., finding some new relationships between the number of vertices and triangles and tetrahedra in shapes. And so here's another way of kind of spinning around that IVM and talking about it. The isotropic vector matrix is a lattice of rods connecting the center of spheres of equal radius. Every sphere is a nucleus surrounded by 12 other in a cuboctahedral conformation. It's not the only option. The rods or stress vectors define tetrahedral and octahedral voids of volume 1 and 4, respectively. The IVM is also known as the octet truss. Octahedra, tetrahedra, and is quite widely used in architecture and engineering. As a uniform dispersion of points in space, the IVM models an ideal gas, freeze frame to define average molecular positions as per Avogadro's law. So here's some cool images of packed spheres and about the way that we get the close packing of spheres and the cubic geometry that arises. Let's turn to Latis in Preyson's blog and just look at a few cool pieces of information. So we're talking in this section about XYZ and IVM, about how they're similar, how they're different, how we get the XYZ from IVM, but not vice versa. So here is a dodecahedron with 20 vertices and an icosahedron with 20 faces, which are kind of duals of each other. And these two shapes are almost hiding these three orthogonal XYZ planes. So everything good that you can say about XYZ, you get that from the planes inscribed within the dodecahedron and an icosahedron as its dual. And this blog post is pretty interesting because it has a big list, not an exhaustive list, of 20-fold paths. 20 popping up all over the place. Insights, strategies, methods, guidelines, principles, rules, 20 rules that everyone can live by, 20 rules for writers and writing, 20 rules of knowledge formalization. So this 20 number comes up all the time, and that's kind of our task to find the meaning of that. Here are some other closed shapes and some similarities so that we can use these as mnemonics just to kind of hold in mind. So here's that dodecahedron with 20 vertices with the all pentagons, and here's another all pentagon shape. It's a soccer, a football, I guess, as the non-Americans call it. And then there's C60, Buckminster Fullerene, the buckyball. And that can be seen as an example of tensegrity architecture, where tension and compression are in balance. Here, some more cool images from the blog post. Here is a way that we can use the number 7, which is going to come back up. Here's a cuboctahedron, and the sides have the questions: who, what, why, where, when, how, etc. And then shapes are provided as mnemonics or kind of investigation devices for exploring those different questions. So it's a geometric way to think about something that doesn't necessarily have an endogenous geometry. And then just one more look at that. Here's those 7 questions: where, how, why, when, who, which, what, where, how, why, who, when, which, what. And those can be rotated around, and they can also be replaced with other sets of 7. So there's 7 axes of symmetry, which are being related to the 7 questions, but that can be also connected to the 7 axes of bias and the 7 pairs of opposites. So personal and impersonal, for example, feeling and thinking. It's not exhaustive, but it's a way to use geometry as a mnemonic as we're navigating these interesting landscapes of thought. That's kind of what Synergetics is about. It's the geometry of thinking. In another latest impressions.org post, the 20 amino acids, so we talked about 20 on the previous page, there's 20 common or base amino acids. And what does that have to do with anything? Well, we can think about those two duals, the 20 vertex and the 20 face shape, the dodecahedron and the icosahedron, and then map those onto the codon table and the amino acids, as well as to other things where there's 20 of them, like the G20, the big economy groups of countries. So this just gets us used to thinking not in terms of a list or a grid, which is kind of that open-ended XYZ mentality, but rather thinking on topologically closed surfaces. Here's a really nice graphic, and I wish it were interactive and tied with computational ontology and could do so much more, but it's the tetrahedron right at the center. The tetrahedron is the minimum polyhedra. So in this map of polyhedra, it makes sense that it would be like right in the middle. And then there's a few ways that we can explore this image. So here's one of them. Here's where the shapes, the names of them have been removed. So instead of calling the 32 facet, 90 edge, and 60 vertex shape the truncated icosahedron, we can just call that one the 182, the 2 times 7 times 13 here, and see some other different relationships between the shapes. And here's another way that you can kind of slice that. Now, the names are back, and we can think about these paths that connect through the tet right in the middle. So we have this kind of one world up here with the Cuboctahedron, the vector equilibrium, as well as a bunch of other shapes, and then another world down on the bottom, and then it kind of comes through the tetrahedron. That's like our meeting point in the middle. So, cool geometry. And then one last thing here from the latest impressions on the theme of mnemonics. So here is the 4 Platonic polyhedra configured around a tetrahedron. So it's just a memory device. It's not saying this is some special significant shape. And then on the right is the indication of the 12 Archimedean polyhedra, the truncated shapes, configured around truncated polyhedron. So, truncated tetrahedron, sorry. So that's kind of just an interesting way that we can, again, thinking in terms of closed topological geometric spaces rather than just sort of lists or grids. And then there's the close packing, which we're going to be exploring a lot. The packed spheres make an icosahedron, and then they can be packed and unpacked. And then just to highlight one of those lists of 20 that are in the blog, here are the 20 hindrances according to Buddhism: belligerence, resentment, concealment, spite, jealousy, miserliness, deceit, dissimulation, haughtiness, harmfulness, non-shame, non-embarrassment, lethargy, excitement, non-faith, laziness, non-conscientiousness, forgetfulness, non-introspection, and distraction. So just kind of some cool things to think about when we're learning synergetics. Let's jump into the text, section 402, tetrahedron as system. 402.1. The tetrahedron as a real system consists of one concave tetrahedron and a second convex tetrahedron, plus a third tetrahedron for all the universe outside the system as tetrahedron, and a fourth tetrahedron complementary accounting for all universe inside the system as tetrahedron. All the angles are the same on the inside as on the outside. So first, it's interesting that the is used in relationship to universe, but this is kind of like taking tet thinking to the extreme, where we're going to think about the closed tetrahedron. That's kind of the one you hold in your hand, but it's also carving another tetrahedra out from the rest of universe. And here's the more simple definition. A tetrahedron is a triangular faceted polyhedron of 4 faces. It is unique as a system, for it is the minimum possible system. So that's sort of the go-to meme for why should we be tet-centric, because it's the minimum system. 403. Stable and unstable systems. There are stable systems and unstable systems. For a discussion of stable and unstable structures, see section 608, Stability, Necklace. So, just to recall, the idea here was that we were going to be stringing these beads that are kind of like unit length around a necklace, a piece of string. And we find which systems are stable and which ones are not stable. Well, a line is not stable, it kind of waves around. You can make all kinds of other systems that still have degrees of freedom in their movement, but the tet is where you can take those 6 beads and close them, and it becomes stable. Conceptuality. Unstable systems are conceptual as momentary positional relationships of unstructured component event aggregates. For example, among the stars comprising the Big Dipper in Ursa Major, the second and third stars in the Dipper's handle are respectively 100 and 200 light years away from Earth, and though seemingly to us in the same plane, are not all so, and they are both moving in opposite directions, and in due course they will no longer seem to be in the same constellation. In the same way, 4 airplanes flying in different directions may be within visible range of of one another, but are far too remote for mass interattraction to become critical and pull them into one another. Stable systems are conceptual as structured, which means componently intertriangulated, critical proximity, interrelevant, coordinate, constellar events aggregates. So here is just for those who need a reminder. Here's the Big Dipper. And here's the Big and the Little Dipper next to each other. And this idea of synchronous events and simultaneity of events plays out in the awesome book by Bucky, Tetra Squirrel, Goldilocks, and the Three Bears, which is a children's story. And it's available in book form, but it actually was created in this foldable scroll. So you could kind of like unfold it and the scroll would unroll. What is being said about the Big Dipper? So this is kind of like saying, we've all heard people say, well, the stars, we don't know what the current status of the star is. We're getting starlight from so many years ago, but that light is converging on the observer as the center at that one moment. So that's kind of one of the differences between the XYZ and the IVM. In the IVM, we really do have this point in the center where things can converge upon. And then from the point of view of that point, minimum systems, so at minimum 3 other systems where the observer is the fourth point, is like viewing out. And those systems could be very far away. They could be coming towards each other, going apart, but that's the conceptual system. 3. Generalized principles. If the only momentary and optically illusory system consideration proves to be unstable, it does not manifest generalized principle. If systems are stable, they inherent in and accommodate all generalized principles. So this is kind of an interesting idea that stable systems are the most aligned with the generalized principles, say the minimization of free energy or the reduction of distance between the spheres, whereas unstable systems, transiently or in a momentary way, can be positioned in a less structured way. So the generalized principles are like the structuring principles, but things can be far from equilibrium transiently. How does this relate to close packing of rods? So section 412. 1. Just as 6 balls may be closest packed around a nuclear ball in a plane, 6 rods or wires may be closest packed around a nuclear rod or wire in a cluster. When the 7 wires are thus compacted in a parallel bunch, they may be twisted to form a cable of hexagonal cross-section, with a nuclear wire surrounded by the other 6. The hexagonal pattern of cross-section persists as complete additional layers are symmetrically added to the cluster. These progressive symmetrical surroundments constitute circumferentially finite integrities in universal geometry. So here is figure 412.01. So here's like one big steel rod. And then the second column is like that one rod, you shrink it down, and then you pack 6 around it. So it would still fit in the same coating, and then you shrink that one down, and then you add one more shell. So this is called frequency in Synergetics, and it just refers to layering one more layer of balls around a given point. So this is kind of looking at within one plane, we're just making cables that are the same diameter, but then they have more and more and more thinner and thinner and thinner pieces. Surface tension capability. We know by conclusive experiments in measuring that the progressive subdivision of a given metal fiber into a plurality of approximately parallel fibers provides tensile behavior capabilities of the smaller fibers at increased magnitudes, up to hundreds and thousands-fold that of the unit solid metal section. This is because the increased surface-to-mass ratio, and because all high tensile capability is provided by the work hardening of the surfaces. This is because surface atoms are pressed into closer proximity to one another by the drawing tool through which the rod and the wire are processed. So, first point is about compression and tension, and the second one is about having increasingly threaded tensile elements. So, what is the way that elevators work? Do they have a big pedestal that pushes them up from the bottom and pulls and then lowers if you want to go down? Well, no. It turns out that having a big column of metal that could support an elevator would be a very challenging task, and it would be suboptimal for a few reasons, but it also would have to be much more than, let's just say, 1 inch, whereas a 1-inch metal cable can absolutely hold up an elevator. So that's the power of tension versus compression, and that's what tensegrity is about, is recognizing the complementary nature of tension and compressional forces in structural integrity. And so these are like finer and finer weaves of tensile fibers. And we get the tensile strength adding as we make it more and more packed, smaller and smaller fibers at higher and higher frequency. And so having just one steel rod, it has a given tensile strength, but the tensile strength increases as we make smaller and smaller fibers. And so here's kind of cool, like, and also it's funny because the rod's area, it's given as 314.159, which some may recognize as the earlier numbers of pi, but we don't have pi here. It's just given as a number. Now we move from the packing of threads in a bundle to spheres in space. So omnidirectional close packing. In omnidirectional close packing of equiradius spheres around a nuclear sphere, 12 spheres will always symmetrically and intertangentially surround one sphere, with each sphere tangent to its immediate neighbors. We may then close pack another symmetrical layer of identical spheres around the original 13. The spheres of this outer layer are also tangent to all of their immediate neighbors. The second layer totals 42 spheres. If we apply a third layer of equiradius spheres, we find they too can pack symmetrically and tangentially. The number of spheres in the third layer is 92. Equiradius spheres closest packed around a nuclear sphere do not form a supersphere, as might be expected. They form a symmetrical polyhedron of 14 faces, the vector equilibrium. So, we have the zero frequency triangle. This is it's also very interesting. When is it a 1 versus a 0 frequency? But it's given as 0 frequency. So this is just 3 balls on a table next to each other, making one triangle from their center points. This is the 2 frequency triangle. So this is a lot like the rods, but instead of a hex expansion of frequency, we're making layers. We're adding more like Pascal's triangle. So what happens when we take that into 3 dimensions? When we close pack spheres, not in the plane, but in space, we get omnidirectional close pack spheres. And their vertices, as we looked at a little bit earlier, trace out a vector equilibrium. So here's those 3 that make up the triangle part here, and then here's the 4 that make up the square side. So this is what it means to say that space has a shape. When you close pack spheres, you get vector equilibrium, Cuboctahedron, whatever you want to call it, you get this shape. You don't get some other shape. So in whatever scenario we're in here, to whatever extent we understand it, this is the shape of space, or at least telling us something about it. So 413.01. Omnidirectional closest packing around a nucleus. That's the vector equilibrium. Triangles can be subdivided into greater and greater numbers of similar units. The number of modular subdivisions along any edge can be referred to as the frequency of a given triangle. The angle is the one that's independent of size, but frequency is the one that is very dependent on size. In triangular grid, each vertex may be expanded to become a circle or sphere, showing the inherent relationship between close-packed spheres and triangulation. The frequency of triangular arrays of spheres in the plane is determined by counting the number of intervals. A. rather than the number of spheres on a given edge. So that's why we call this one a 2 frequency, but I'm not sure why we call that one a 0 frequency rather than a 1 frequency. In the case of concentric packings or spheres around a nucleus, the frequency of a given system can either be the edge subdivision, or the number of concentric shells or layers. Concentric packings in the plane give rise to hexagonal arrays, just like the rope. And B, omnidirectional closest packing of equal spheres around a nucleus gives rise to the vector equilibrium. So that's kind of giving us a big hint about the shape of space, what happens with triangles and with the VE. If we add on more layers of equiradius spheres to the symmetrical polyhedron of 14 faces close packed around one sphere, we find that they always compact symmetrically and tangentially, and that this process of enclosure may seemingly be repeated indefinitely. Each layer, however, is in itself a finite or complete and symmetrical embracement of spheres. Each of these embracing layers of spheres constitutes a finite system. Each layer always takes the 14-face conformation and consists of 8 triangular and 6 square faces. Together with the layers they enclose and the original sphere center, or nucleus, these symmetrically encompassing layers constitute a concentric finite system. As additional layers are added, it is found that a symmetrical pattern of concentric systems repeats itself. That is, the system of 3 layers around one sphere with 92 spheres in the outer layer begins all over again and repeats itself indefinitely with successively enclosing layers in such a way that successive layers outside of the 92 sphere layer begin to penetrate the adjacent new nuclear systems. We find that then only the concentric system of spheres within and including the layer of 92 are unique and individual systems. We will pursue this concept of a finite system in universal geometry still further. Section 418, etc. In order to relate it to the significance of the 92 self-regenerative chemical elements. So these are the elements up to uranium that are stable. So that's kind of an interesting connection. And this is really a key idea, that we're looking for finite systems only, finite integer systems, in this universal geometric layer. Inside of the IVM, which we know that we can get from here, we want to find finite systems. So whatever the frequency is, whether it's the minimum, the 0 frequency shape, just the single ball at the center, or whether we add a million frequencies, we're still going to have a finite system. So nucleus. In closest packing of equiradius spheres, a nucleus by definition must be tangentially and symmetrically surrounded. This means there must be a ball in every possible tangential and optically direct angular relationship to the nucleus. This does not happen with the first layer of 12 balls or with the second layer of 42 balls. Not until the third layer of 92 balls is added are all the tangential spaces filled and all the optically direct angles of nuclear visibility intercepted. We then realize a nucleus. This is quite an interesting observation, that when you have just this first layer, then there still is like an optical way that you can see the center. And it turns out that even the second layer of 42 balls, you still have not added a blocker for all optical direct angles to nuclear visibility. So it's actually this third layer that realizes a nucleus. And I just wrote hashtag internal states related to active inference, whether that was somehow like, that's when you can truly have a Markov blanket, when you've really made this multi-layer system that can actually have an insulated nucleus. It will also be discovered that the third layer of 92 spheres contains 8 new potential nuclei. However, these do not become realized nuclei until each has 2 more layers enveloping it, 1 layer with a nucleus in it and 2 layers enclosing it. 3 layers are unique to each nucleus. This tells us that the nuclear group with 92 spheres in its outer or third layer is the limit of unique closest packed symmetrical assemblages of unit wavelength and frequency. These are nuclear symmetry systems. It is characteristic of a nucleus that it has at least two surrounding layers in which there is no nucleus showing, i.e. no potential. In the third layer, however, 8 potential nuclei show up, but they do not have their own 3 layers unique to realize them. So the new nuclei are not yet realized, they are only potential. So these are very much restatements of each other. And it's getting at that same idea that as you start to add frequencies, add shells around the initial nucleus, when you get to the third one, you have created a nuclear symmetry system. Then you've created some almost nuclei, but then you need another shell to realize those as true nuclear symmetry systems. The nucleus ball is always 2 balls, one concave and one convex. The 2 balls have a common center. Hydrogen's one convex proton contains its own concave nucleus. Concentric shell growth rates. Minimal, most primitive concentric shell growth rates of Equiradius closest packed symmetrical nucleated structures. Out of all possible symmetrical polyhedra producible by closest packed spheres agglomerating, only the vector equilibrium accommodates a 1-to-1 arithmetical progression of frequency number and shell number developed by closest packed Equiradius spheres around one nuclear sphere. Only the vector equilibrium equanimity accommodates the symmetrical growth or contraction of a nucleus-containing aggregate of closest packed Equiradius spheres characterized by either even or odd numbers of concentric shells. So, for other shapes, if you added spheres around them, there might be a part where you needed to double up or it wouldn't perfectly fit. But the vector equilibrium we can grow by kind of crystallizing these shells around it just indefinitely. 3. Odd or even shell growth. The hierarchy of progressive shell embracements of symmetrically closest packed spheres of the vector equilibrium is generated by a smooth arithmetic progression of both even and odd frequencies. That is, each successively embracing layer of closest packed spheres is in exact frequency and shell number attunement. Furthermore, additional embracing layers are accomplished with the least number of spheres per exact arithmetic progression of higher frequency. Even number shell growth. The tetrahedron, octahedron, cube, and rhombic dodecahedron are nuclear agglomerations generated by only even-numbered frequencies. Here's some of the equations that are given in Synergetics with the nuclear symmetry systems and at what point they actually realize that third shell. And then here's those equations from Dick Fishbeck et al. From earlier in the discussion. And here we see like that 10f squared plus 2. Here's 10f squared plus 2. That's the number of shells as we go out. So the 0th shell. And then 0 equals 2. That's brought up later in some of the numerology sections. But also that's sort of to make this equation work for even f equals 0. And then we have sequences of numbers. And we can see that the vector equilibrium, it's like always working. Every shell, we can continue with the same equation, but other shapes, they might work for a given shell, but then they don't work for all shells. So maybe another time, especially if somebody could share more expertise, we could talk more about nuclear synergetics. So that was the tetrahedron as a system. We've talked about tetrahedron as minimal system, and there's a few other sections on that in a few other synergetic streams, and of course other work as well. But that was a little bit of a different look at tetrahedron as a system because we talked about the tetrahedron as the stable system and as one that can be reached at from close packing, like 4 balls close packed make a tetrahedron, and then the vector equilibrium is sort of the core shape there. So let's go to section 1230 for the Scheherazade numbers. So this is going to be a little bit at the end of Synergetics, very close to the end. This is where it gets a little numerological, but this is kind of a fun sequence and Also one, of course, just like they all are, that's really open to interpretation and exploration. So if you have any thoughts on this, just leave them in the live chat or give a thought. 1230.10. Prime number accommodation, integration of 7. The Babylonians did not accommodate a prime number like 7 in their mathematics. Plato had apparently been excited by this deficiency, so he multiplied 360 by 7 and obtained 2,520. And then, seeing that there were always positives and negatives, he multiplied 2,520 by 2 and obtained 5,040. Plato apparently intuited the significance of the number 5,040, but he did not say why he did. I am sure he was trying to integrate 7 to evolve a comprehensively rational circular dividend. So in other words, how do we get the nice divisibility that we get, for example, with 360, but where's the 7? So how do we reintegrate 7-ness into our geometry systems? 1230.11. H2O is a simple low number. As both chemistry and quantum physics show, nature does all her associating and disassociating in whole rational numbers. Humans accommodated the primes 1, 2, 3, and 5 in the decimal and duodecimal systems, but they left out 7. After 7, the next two primes are 11 and 13. Human superstition considers the numbers 7, 11, and 13 to be bad luck. In playing dice, 7 and 11 are crapping or dropout numbers, and 13 is awful. But so long as the comprehensive cyclic dividend fails to contain prime numbers, which may occur in the data to be coped with, irrational numbers will build up or erode the processing numbers to produce irrational, ergo unnatural results. We must therefore realize that the tables of trigonometric functions include the first 15 primes. 1, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 41, 43. Okay, so a few themes here. 7, 11, and 13, which we're going to be talking a lot about, have kind of been given a little bit of a ignored role, potentially because the number systems that we have work well with a few other primes, but we didn't capture every prime. And numbers that aren't prime, we can get at from primes. That's like basically the definition. And so we want to have an integer accounting system that can at least handle the primes up to 45. And we'll see why 45 soon. 12. We know 7 times 11 is 77. If we multiply 77 by 13, we get 1,001. Were there not 1,001 tales of the Arabian Nights? We find these numbers always involved with the mystical. The number 1001 majors in the name of the storytelling done by Scheherazade to postpone her death in the 1001 Nights. The number 1001 is a binomial reflection pattern, 1, 0, 0, 1. So we take all those three kind of ignored numbers, 7, 11, 13, and multiply them together, we get 1001. SSRCD numbers. If we multiply the first four primes, we get 30. If we multiply 30 times 7, 11, and 13, we have 30 times 1001, or 30,030, 30, 30, and we have used the first 7 primes. We can be intuitive, so the first 4 primes are how we get up to 7. So that's like the first 4 primes, 1, 2, 3, and 5. We can be intuitive about the 8th prime, since the octave seems to be so important. The 8th prime is 17, and if we multiply 30,030 by 17, we arrive at a fantastically simple number, 510,510. This is what I call an SSRCD number, which stands for Scheherazade Sublimely Rememberable Comprehensive Dividend. As an example, we can readily remember the first 8 primes factorial. 510, 510, exclamation point. Factorial means successively multiplied by themselves. Ergo, 1 times 2 times 3 times 5 times 7 times 11 times 13 times 17 equals 510,510. So this is a little bit of number play, but it turns out that by giving these special primes their due, we can get these mnemonics for thinking about large numbers, and there's going to be some big implications for that. 30. Origin of the Scheherazade myth. I think the Arabian priest mathematicians and their Indian Ocean navigator ancestors knew the binomial effect of 1001 upon the first four prime numbers 1, 2, 3, and 5, and did indeed provide comprehensive dividend accommodation of all the permutative possibilities and all the story-telling, tallying, or computational systems of the octave system of integers. So it's kind of cool to think about storytelling and telling tales and tallying. These are all kind of coming together in, of course, the 1001 Arabian Nights. The function of the Grand Vizier to the ruler was that of mathematical wizard. The whiz of wisdom and the wizard kept secrets to himself. The mathematical navigational ability to go to faraway strange places where he alone knew there existed physical resources different from any of those occurring, quote, at home. Then voyaging to places that only the navigator priest knew how to reach. He was able to bring back guaranteed strange objects that were exhibited by the ruler to his people as miracles obviously producible only by the ruler who secretly and carefully guarded his vizier's miraculous power of wisdom. So, very interesting. It's kind of like in the world of sense-making, the sense-maker is the wizard. In the world of navigation, the navigator is the wizard. To guarantee their own security and advantage, the Mesopotamians mathematicians, who were the overland and overseas navigator priests, deliberately hid their knowledge. Their mathematical tools and operational principles, such as the mathematical significance of 7 times 11 times 13 equals 1001, from both their rulers and the people. They used psychology as well as outright lies, combining the bad luck myth of the 3 prime integers with the mysterious inclusiveness of the 1001 nights. The priests warned that bad luck would befall anyone caught using 7, 11s, or 13s. Some calculations could only be done by the abacus or by positioning numbers. With almost no one other than the high priest able to do any calculation, there was not much chance that anyone would discover the product of 7, 11, and 13 is 1001. But just in case, they developed the diverting myth of Scheherazade and her postponement of execution by her 1001 nights. Okay, so we pivot from this idea of 1001 as a special number that's kind of like the 3 missing primes. 7, 11, and 13 combine, multiplying to get 1001. Pivot from there back to the West. So, 1231.0, Cosmic Aliens. Western world humans are no longer spontaneously cognizant of the Greek or Latin number prefixes like des or non or oct, nor are they able spontaneously to formulate in appropriate Latin or Greek terms the larger numbers spoken of by scientists nowadays only as powers of 10. On the other hand, we are indeed familiar with the Anglo-American words 1, 2, and 3. Wherefore we may prefix these familiar designations with a constant ilian suffix, which we will now always equate with a set of 3 successive zeros. So the ilian is kind of like our codon of 000. So it's like a power of 1,000 is an ilian. 2. We used to call 1,000, 1,000. Oh, there I did it again. Let me start again. We used to call 1,000, 1,000. We will now call it 1 ilian. Each additional set of 3 zeros is recognized by the prefixed number of such 3 zero sets. 1 million equals 2 ilian. 1 billion is 1 3 ilian. This is always hyphenated to avoid confusion with the set of sub-billion enumerators, e.g. 206 4 ilians. The English identified ilians only with 6 zero additions, while the Americans used ilians for every 3 zeros, starting, however, only after 1,000, overlooking its 3 zeros as common to all of them. Both the English and American systems thus were forced to use awkward nomenclature by retaining the word Initial word thousand as belonging to a different concept in a historically earlier time. Using our consistent Ilian nomenclature, we express the largest experientially conceivable measurement, which is the diameter of the thus far observed universe measured in diameters of the nucleus of the atom, which measurement is a neat 312.14 Ilians. So, if we take the scope of the observed universe and then divide that by the nucleus of the atom, so that's a finite number by a finite number, we get this number 312.14 Ilians. So, 14 sets of 3 zeros. Okay, so this is an interesting little excursion into numbering. How do we talk about numbers? Do we talk about them in terms of powers of 10 or powers of 1,000? And we'll just use Ilian to refer to bumping up the power of 1,000 by 1. So, binomial symmetry of Scheherazade numbers. Exponential powers of 1,001. As with all binomials, for example, a squared plus 2ab plus b squared, the progressive powers of the 1001 Scheherazade numbers produced by 7 times 11 times 13, the product of which, multiplied by itself in successive stages, produces a series of symmetrical reflection numbers. They are not only sublimely rememberable, but they resolve themselves into a symmetrical mirror pyramid array. So, the binomial symmetry expands all of its multiples in both left and right directions in reflection balance. Note that the exponential power to which the 1001 Scheherazade number is raised becomes the second whole integer from either end. As with a plus b squared equals a squared plus 2ab plus b squared, the interior integers consist of expressions and products of the exponent's power. So here's 1001 squared. We get 1002 as kind of the middle point, and then 001. So it's a mirror around 2. And so you can see that there are a lot of mirroring things happening with these numbers, which we'll explore more in the next few slides. But also it's kind of cool, like looking down the pyramid, you get like 2, 3, 4, 5, 6, 7, 8, 9, and then 10. Cancellation of leftward spillover. In the pyramid array of 1001 Scheherazade numbers, we observe that due to the double symbol notation of the number 10, the symmetry seems to be altered by the introduction of the leftward accommodation of the two integers of 10 in a single integer position. So we can look back at 1001 to the 5th power. So here's 1001 to the 5th power. 1005, 010, 010, 005, 001. This number, it's going to get pulled out so that the 1 kind of comes above the line. And then it's like a much better mirror. So Bucky is suggesting 10 could be written vertically as like 1 and 0. So it's kind of like carrying over when you do the multiplication and then, okay, now we got a 1 up here, so let's spill it over to the left. What if you just leave it there? Instead of 10, provided we always assumed the vertically superimposed integer was to be spilled into the addition of the next leftward column, for we build leftward positive and rightward negatively from our decimal 0, 0. The abacus with its wires and beads taught humans how to fill a column with figures, and thereafter to fill additional columns by convention to the left. The Arabic numerals developed as symbols for the content of the columns. They filled a column and then they emptied it, but the cipher prevented them from using the column for any other notation, and the excess, by convention, was moved over to the left. This spillover can begin earlier or later depending on the modulus employed. The spillover to the next column begins later when we are employing modulo 12 than when we are employing modulo 10. To disembarrass the symmetry of the leftward spillover, the spillover number in the table has been written vertically. So, just like you'd imagine that you'd need to start carrying numbers, spilling them over very soon in base 2, and in base 10, that's kind of the one that usually we're most familiar with. We spill over at when we get the 1, when we get 10 in a given position. But what if each position could hold 100? Then you wouldn't have to spill over until you were at 100. The table of the 10 successive powers of the 1001 Scheherazade numbers accidentally discloses a series of progressions. 1. In the extreme right-hand column, a progression of zeros. 2. In the fourth column from the right, an arithmetical progression of n squared minus n over 2, which we call triangular. And 3. In the seventh column from the right, a tetrahedral progression. So here's what that looks like. This is raising n, 1001, to different powers. So here in this fourth column, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, and then spillover. But we're going to leave that 1 up top. In the fourth column from the right, so it's going to be this one, so kind of at the millions place, you have 1, 3, 6, 10, 15, 21, 28, 36, 45. So by keeping that number up top, we reveal, I guess that's the accidental disclosure. Whoops. That's where you get the arithmetical progression. And then in the seventh place, we get tetrahedral numbers. 1, 4, 10, 20, 35, 56, 84, 120. 23. The tetrahedron can be symmetrically or asymmetrically altered to accommodate the 4 unique planes that produce the fourth dimensional accommodation of the vector equilibrium. The symmetry disclosed here may very well be 4-dimensional symmetry that we have simply expressed in columns in a plane. The number 1001 looks exciting because we are very close to the binary system of the computers. We remember that the Polynesians only counted to 1 and 2. The binary yes-no sequence looks so familiar. The Scheherazade number has all the numbers you have in the binary system. The 1001ness keeps persisting throughout the table. So here we keep on seeing like 1 and 1. And then this 1001ness keeps on continuing once we've accounted for all these other special columns. The numbers 7 times 11 times 13 times 17, included in the symmetric dividend 510,510, may have an important function in atomic nucleation, since it accommodates all the prime numbers involved in the successive periods. So now let's look at some big numbers. Okay, so this is a little bit of a different, not a contradiction, we'll call it a contrary, because it's different than the previous claims that 1 is a prime. Many mathematicians assume that 1 is not to be counted as a prime. Thus, 2, 3, 5, 7, 11, and 13 make a total of 6 effective primes that may be identified with the fundamental vector edges of the tetrahedron, and the 6 axes of conglomeration of 12 uniradius spheres closest packed around one nuclear sphere, and the fundamental topological abundance of universal lines that always consist of even sets of 6. So, this is where it gets a little bit into the mnemonics, because it's kind of like thinking, well, we can remember those first 6 primes, other than 1, as being like corresponding, kind of like the latest in Preyson's blog post that we looked at, corresponding to the edges of the tet and the 6 axes in the vector equilibrium. And so then this table 1232.30 gives a lot of Scheherazade reflection patterns. So here's kind of a bunch of ways to take that same ordering of primes and just get a bunch of interesting findings. So here's that 510, 510. Here's the 1001. We talked about 30,030, and there's just a bunch of other numbers. So they're kind of like fun ways to get big numbers. What about the 7 Ilian Scheherazade number? The 7 Ilian Scheherazade number includes the first 7 primes, which are 1 times 2 times 3 times 5 times 7 times 11 times 13 to the 5th power. Then that is taken to the 5th power. And then here's that large number provided here. Cool number, Bucky. In the first days of electromagnetics, scientists discovered fourth power energy relationships, and Einstein began to find fifth power relationships having to do with gravity accommodating fourth and fifth powering. The first 7 primes factorial is a sublimely rememberable number. It is a big number, yet rememberable. When nature gives us a number we can remember, she is putting us on notice that the cosmic communication circuits are open. You are connected through to many sublime truths. So even if you can only remember the number 4 or 1, that's okay. You're still on notice. Though factored by 7 prime numbers, it is expressible entirely as various size increments of the 3 to the 5th power. There is a 4-place overlapping of 1. 3 to the 5th power means 5-dimensionality triangulation, which means that 5-dimensional structuring as triangulation is structure. We'll look at it in a second. And then just 04. When this number, when it is substituted as a comprehensive dividend for 360 degrees and 0 minutes or seconds to express cyclic unity in increments equal to 1 second of arc, while recalculating the tables of trigonometric functions, it is probable that many, if not most, and possibly all the function fractions will be expressible as whole rational numbers. The use of that long number as cyclic unity will eliminate much cumulative error of the present trigonometric function tables. So let's look at that number. Okay, so here is the number itself. And now, just as we kind of saw where we could take a number and then like vertically expand it, like here this 4 is a 4, but this 4 is expanded into a 3 and a 1. So that's like the leftward spillover of the 1 and then a 3. And so that big number, which was here, 24,421, which doesn't immediately look like it has any mirrors or symmetry inside of it. When you break it down this way, we can see there's like this 243, 243, which is 3 to the 5th. 243 is 3 to the 5th. So you get 3 to the 5th twice. That's like the nucleus. Then there's 2 12/15s with the leftward spillover. That's 5 times 3 to the 5th. Then there's other 243s on the shoulders. So it's like, whoa, that's an interesting number. And what Bucky's saying here is the degree of precision that makes sense for an engineer is like, if you could only talk in degrees, that's probably not enough to be precise. And then you have like the hours and the minutes, or the minutes and the seconds. So if you could have, like this is the trigonometric tables. Even though we have calculators today that you could have like fractions of a second. If you can get this, you'll be able to do a lot. And he's saying, well, maybe this number's big enough so that all of these, so 360 times 60 times 60, that might fit rationally in here. So we wouldn't even need fractions. Here, so that's the 7 Ilian Scheherazade number. Let's look at the 8 Ilian Scheherazade number. So the 8 Ilian Scheherazade number is given by this equation. So it's 1 times 2 cubed times 3 to the 8th times 5 to the 5th times 7 to the 4th times 11 to the 3rd times 13 to the cubed to the 3rd power, times 17 squared times 19 times 23 times 29 times 31. And here's the big number. It starts with a 1 and it ends with a 0. The 8 Ilian Scheherazade number accommodates all trigonometric functions, spherical and planar, when unity is 60 degrees. Its halfway turnabout is 30 degrees. It also accommodates the octave 90 of the icosahedron's corner angles of 72 degrees, 1/2 of which is 36 degrees. Ergo, 31 is the greatest prime involved. Here's the 31. Which characterizes maximum spherical excess of the vector equilibrium's 60 degrees. And then here is the 9 Ilian number. And here is another number sequence with some other interesting relationships. So like just like we had like 243 kind of here twice, here's 658. And then 806 and 608 are like a mirror. And then here is 58 and 29. And so 2 times 29 equals 58. So yes, it's number play, because it's not like it's just a palindrome. It's not exactly a palindrome. It's more like there are ways in which you can link across, but still interesting nonetheless. So what about that 14 illion? So we got up to 9, 7, 8, and 9. All looked pretty cool. Let's take it to the 14 illion Scheherazade number. So remember, an illion is like 3 zeros. It's a codon of zeros. So we're going to take it to the 14 illion. Trigonometric limit, first 14 primes. The 14 illion Scheherazade number accommodates all of the omnirational calculations of the trigonometric function tables, whose largest prime number is 43 and whose highest common variable multiple is 45 degrees, which is 1/8 of unity in a universe whose polyhedral systems consist always of a minimum of 4 positive and 4 negative quadranted hemispheres. So why does 45 matter? Why are we going to take it up to 45? Here's why. 45 degrees is the zero limit of covarying asymmetry because the right angle's 90-degree corner is always complemented by 2 corners, always together totaling 90 degrees. The smallest of the covarying 90-degree complementarities reaches its maximum limit when both complementarities are 45 degrees. Accepting the concept that 1 is not a prime number, we have 14 primes. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, which primacy will accommodate all the 14 unique structural facetings of all the crystallography, all the biological cell structuring, and all bubble agglomerating. The 14 facets being the polar facets of the 7 and only 7 axes of symmetry of universe, which are the 3, 4, 6, 12 great circles of the vector equilibrium and the 6, 10, 15 great circles of the icosahedron. So 45 degrees is kind of like the crossover point for angles. So working within the 360-degree system, once you're like 45 degrees away from one side, then you start getting less than 45 degrees from another side. And that will be explored more in 23. So 22. Tetrahedral complementations. The sphere to space, space to sphere intertransformabilities is a conceptual generalization holding true independent of size, which therefore permits us to consider the generalized all-space-filling complementarity of the convex sphere and concave space octahedra with the convex sphere and concave space vector equilibria. This also permits us to indulge our concentrated attention upon local special case events without fear of missing further opportunities of enjoying total synergetically conceptual advantage regarding non-simultaneously considerable scenario universe. There's probably so many ways to read this, but a few things that really jump out. So we're indulging, we're enjoying. It's our regime of attention. We are choosing where to put our attention, we hope. And these are all kind of like descriptive facts about the world or about numbers or whatever. And so it's really about where we put our attention and then how we apply our attention, given those generalized principles, to local special case events, like these 4 balls on the table. And that is what allows us to enjoy a conceptual advantage, because we can't think about it all at once. It's non-simultaneously considerable. But if we can concentrate our attention and bring the right generalizations to the right specific cases at the right time, we will enjoy every opportunity synergetically. 23. We know the fundamental intercomplementations of the external convex macrotetra and the internal concave microtetra with all conceptual systems. Looking at the 4 successive plus minus XYZ coordination quadrants, we find that a single 90-degree quadrant of one hemisphere of the spherical octahedron contains all the trigonometric functioning covariations of the whole system. When the central angle is 90 degrees, then the two small corner angles of the isosceles triangle are each 45 degrees. After 45 degrees, the sines become cosines and vice versa. At 45 degrees, they balance. Thereafter, all the prime numbers that can ever enter into prime trigonometric computation, in contradistinction to complementary function computation, occur below the number 45. What occasions irrationality is the inability of dividends to become omni-equidivisible due to the presence of a prime number of which the dividend is not a whole product. So this last sentence is kind of like a statement about prime numbers. It's like saying you get an irrational number when there's something prime that can't be divided by what you're trying to divide it by. So that's why the Scheherazade numbers are based on prime numbers. Because if we only get irrational blockings from prime numbers, let's use all the prime numbers we can. Okay, now why 45? Not totally sure about this, because it seems like, what if we had another system with 3,600 degrees around the circle? Would we have to go to a higher number? Or would we just go to 450 or something like that? But in either case, whether we think about this as sines and cosine, like once you are taking the sine, okay, it's like the y value, and then all of a sudden you can flip it and it's like the x-axis on the other side. And another way of looking at it, rather than just sort of like around the unit circle, is about an isosceles triangle, or just triangles in general. So the triangle, the angles of an isosceles, when you have that right triangle at 90 degrees, which is the basis of trigonometry, like SOHCAHTOA, then there's one special case with a 45 degree and then the right triangle, like an isosceles right triangle. But then any other right triangle, one of the angles is going to be less than 45. This is why we factor completely or intermultiply all the first 14 prime numbers existing between 1 and 45 degrees. Inclusive of these 14 numbers, we multiply the first 8 primes to many repowerings, which produces this Scheherazade number, which when used as the number of units in a circle, becomes a dividend permitting omnirational computation, accommodation of all the variation of all the trigonometries of universe. Okay, so we only get irrational numbers when we get blocked by a prime. So if we multiply a ton of primes together up to the number that makes sense given isosceles right triangles, then we'll be able to have finite rational integer values, because we'll be like, instead of having a sine function that just appears to go off in forever, maybe if we actually divided it by this number, it would be clean. And then here's one last point. The 4 vertexial stars A, B, and C, D, so 4 points of a tet, defining the minimum structural, ergo triangulated system of universe, have only 4 possible triangular arrangements. There are only 4 possible topological vertex combinations of a minimum structural system: ABC, ABD, ACD, BCD. In multi-frequenced modular subdivision of minimum structural system, the subdividing grid may develop 8 positive and 8 negative aspects. So here are, for the minimum system, which is a tet, there's basically 4 triangles. That's the omnitriangulation. There's 4 minimum triangles in the tetrahedron, and then each of those has like a convex and a concave. And so that's why there's hashtag mnemonics here, because these are like all incredible memory and attention tools that help us navigate these ridiculously large numbers. But maybe it also says something pretty deep about the shape of thinking. So, a little bit different today. Hope that it was coherent and enjoyable because it was like two slightly more esoteric sections. But we talked about memes and mnemonics for XYZ and the IVM, isotropic vector matrix coordination systems. And then we talked about the tetrahedron as a system and the Scheherazade numbers, at least one pass on them. So thank you everyone for watching. If you've made it this far, just congrats. So hope you write a comment or get in touch with me or just let me know what you are enjoying or not. Thanks again for watching, and see you on the other side of the Tet.